Hello. Go. You got that selected and running now? Great. Awesome. Yeah, so my name is Shanti. You're in Apex LA, and this is a Hungarian social club in downtown LA. Unless you're watching this on YouTube, in which case, hi. These conference talks are at least a little bit about establishing a personal brand, whatever that means. And if you've seen me at previous talks, you've associated me with like stupid meme jokes and performance in Erlang and advocating for people to write more code in C. And I'm also a bit of a fatalist, but we're going to get back to that later. So yeah, that's my information stuff. I'm going to try and go a little bit quickly so we can catch up on time just a little bit. But yeah, so let's see. That's this talk, High Performance Data Structures in Erlang. The pitch title, is that. But I'm going to be using Erlang and Elixir a little interchangeably for the remainder of this talk. I think all of the talks before me have done a great job of explaining why those are two pretty easy languages to conflate. I'm just going to take advantage of that. I've written enough of both to be forgiven. Oh, geez, I just zoomed through all the slides accidentally. There we go. Bam. TLDR of this talk. Operator library, it's called FDS. You can use it right now. It's on Hex. FDS stands for Functional Data Structures, or maybe Fast Data Structures, depending on how you feel about it. So it's notably not malware. That's a key feature. And in addition to not being malware, nobody can inject a malware dependency into it because it has no dependencies. It just relies on the Erlang and Beam runtimes. It also operates faster than Erlang, asterisk. Every use case is a little bit different, but in some of the ones that I've tested out, the data structures I use are faster than things like the built-in Erlang queues library or queues module. I'd say right now it's probably safe for experimental use. You'll notice that the first number there is a 0 and not a 1. And I think probably there's an array module I'll cover later that's pretty much production ready, but everything else still needs work. Cool. And this is the point where all the YouTubers can go and click on the link in the description and comment, like, subscribe to my Patreon, Ko-fi. And everyone else, I want to talk about my motivation behind doing this. So that's a little morbid sounding, but it's because time is finite. We are all going to die. That's just a fact. And, this means that doing the same amount of things in less time is good. And if I figure if I can spend my time to make something fast and performant for other people, they can spend less of their time worrying about that. And I've, got net extended the longevity of humanity by a couple of seconds. So that feels pretty good in 2020. So I'm constantly asking myself how I can go faster. And this is really uncooperative. Why are you doing this to me, bud? There we go. Yeah. Cool. So yeah, the biggest problem I run into in Elixir is that we kind of can't. We're hamstrung, not hamstrung, but we are limited by the Beam VM. Any given Beam instruction at the SSA stage, because this is an interpreter, takes a lot more than one native processor instructions to run and to execute. So we've got that going against us. As well as the fact that we have no notion of pointers that we can work with in this language, which prevents entire sets of data structures like skip lists or union find data structures from being implemented or being used as simply or as efficiently as you could in something like Java or like C. And there's a reason behind this. Erlang designers did this to maintain simplicity in the message passing in the language, and also to help maintain its immutability contract. And let's see, we talked about mutability. Yep. This immutability means, whenever you change a value in a data structure, you're idiomatically within the language receiving a new instance of that entire structure. And this sounds all pretty dooms and glooms. But under the hood, the Beam optimizes a lot of these instructions and operations when it's able to in ways that are actually well documented, but in the dark recesses of the standard library reference and also in the dusty corners of Erlang change logs. But if you take advantage of these optimizations and also by using some of the newer functional data structures that have come up in popularity over the past couple decades, I achieved some solid speed ups. So I'm going to talk about those. And there we go. So all three of the data structures I'm going to be talking about are container types, which means they contain various elements of data. And some of them specifically are sequences, which means that they've got a concept of like a left and a right, or a front and a back. And all the elements are in an order, not necessarily a sorted order, but they have that relationship with each other. Erlang lists are sequences. They're also implemented extremely simply. They're very small in size, and they've got a very efficient constant time access to the front of the list. So if you want to access it as a stack, it's a perfectly fine data structure for that. However, accessing elements in the later parts of lists gets really slow because you have to iterate through every single element in the list. So when you were running, sometimes we work in applications where we want to work with like a first in, first out data structure, a queue type. And I think the three most common approaches I've seen in the wild have been using lists anyways, which works pretty well if your size is pretty small and you just like kind of can eat the overhead, and it doesn't really matter because if you're iterating through like 10 elements, who cares? And the another approach I've seen is one that I think GenStage, correct me if I'm wrong, relies on, which the queuing mechanism there relies on the Erlang process mailbox, which acts like a queue and kind of takes care of it for you. And given that processes are lightweight compared to OS processes, this seems pretty good. But in terms of memory footprint, they're actually like moderately heavy, certainly compared to like raw Erlang terms. And lastly, and I think covered also earlier today, you see I/O lists in I/O-bound applications, or like in the Cowboy server, which is a representation of binaries consisting of binary data themselves, as well as integer, byte values, and just nested series of lists. These work really well, actually, for the use cases of sequencing I/O bytes or print formatting or whatnot. But there's no actual way to represent list items themselves within that data structure. So that's a trade back. It's sort of inherently limited. So in our use case for a queue, when you're making a game or a pipeline or whatnot, you want to make sure that say in a game you've got an event queue, or in sort of some event processing pipeline, you want to make sure your events stay in order. To push elements into the back of the queue and to pull them out from the front of the queue is kind of like the semantics we're looking for here. The way to build a queue when all you've really got, though, is simply linked lists, is to basically you end up using those linked lists to form trees, and you can use those trees to represent sequences themselves. And that sounds really wacky and weird, but and I found the data structure is called a finger tree. And this is something that Haskell uses as well for its sequence type. But the intuition behind it's a little strange. I think it's easiest for me to use this scarf as a prop and to assume that this is like a sequence of events that are kind of like coming in this direction. And I want to have efficient access to both ends of this data structure so I can put them in here and take them out here. And what we end up doing is just kind of like folding in the middle and it's a little hairy, but yeah, it kind of ends up looking like that. So events are slowly coming in, and we unfold just a little bit when we try to take them out, and we fold them a little bit more when we put elements in. And that's basically how a finger tree works, in addition to keeping me warm. And yeah, so this module has been implemented. It's got that name, FDSQ, and it works. Depending on which use cases exactly you're looking at, it's either faster than or slower than, attempting to just use lists and reversing them to get queue-like semantics. But please try it out and see how it feels, and see if it's faster for your use cases. Yeah. Next up, there we go. So we've got arrays. Arrays also exist in the Erlang standard library. And as opposed to having efficient access to both ends, you want efficient access in the middle, or really anywhere. And indexed access is the kind of thing we take for granted in a lot of C-like languages, and it's pretty lacking in Elixir. If you try to use list or enum.at with just raw lists, you know it's like pretty painful. And I personally wanted a data structure that functions like this, a growable array type object, when implementing Raft in Erlang. So it's just been that Raft implementation has been stalled out a little bit, but one of the things I want to be able to do is to be able to visit locations in history in this like ever-growing list. So what we do have is we have maps in Erlang, and maps do give us that index access, and they are fairly efficient memory-wise, but they don't have any provision for automatically adding keys with an auto-increment counter. You have to build that on it yourself. That might actually be the most efficient way to go with this. But instead, I used an example from the Purely Functional Data Structures book by Chris Okazaki. And it's a data structure called the random access list, which is a list that has random access. It can grow and shrink from the front, and it can be accessed randomly in the middle in log n time. So it's a combination of an array and a list, and I call it a list array because indexed access is not actually super useful if you're constantly adding and removing from the front, because all your elements are shifting around, and so you can't really consistently, like, whatever's at index 2 changes to index 3 when you insert an element. So I created another data type built on top of that just, called the array list, which if you've used Java or in C++, they have the vector type. It functions exactly the same way in terms of semantics. You add an element on, it'll be in position 1. In terms of our sequence model, we're adding and removing from the back of the sequence now instead of the front. And yeah, in terms of performance, it's slower than regular lists at adding and removing elements, but way faster at random access. And compared to the Erlang array type, it is slower at random access, but you can conveniently add and remove elements. So if you're looking for both of those features and don't mind taking a slight penalty hit, this is probably the data type for you. And as I mentioned earlier, I think there is some room for improvement here to move to a model that's backed by a map and a counter. So I would just love to play around with that a little bit more. Cool. Boop. There. And we're going to move on to heaps. So far we've talked about efficient access based off of the position of the data in our sequence. And I want us to look at an example of something like an online high score list for your video game, where players submit scores kind of constantly from whenever they're playing, and we only want to display the top n scores. I think one way to address this that most people probably end up reaching for is just you have the events come in and you sort them, and then you display the first however many elements of what you've sorted. But the time to sort is comparable to the amount of data that you've got to sort. And if your number of players or your number of scores being received just grows really, really rapidly, that sorting is going to get really expensive, even though you still only want to display the top 100 scores. So a heap data structure lets you maintain a mostly sorted order, and you can easily get the maximum or minimum of the values in the heap. And these are referred to as min heaps and max heaps. In terms of our sequence diagram, it's best to think of them as having a front that always has the minimum or maximum element, but they don't quite have a back. They just kind of have a semi-sorted blob of entries in the back. And yeah, let's see, do I have time to go in? I think I might have time to live demo something, so we're just going to give this a shot and see how it goes. Okay. All right, so I'm going to create a demo thing. I already have a demo thing. All right. MPEX 2020. Oh. And we're just going to create, look at our depths here, add FDS 0 to 1, and cool, yeah. So as you see, still in progress, has compile warnings, etc. But let's say we take in, there we go. So let's have our enum dot shuffle. Let's just shuffle 10 numbers and see what we can do. So if we take our scrambled set of numbers and we put it into our Q FIFO type, to s.q.new. Yeah, so we got our queue and everything's in order. And we can pop things off of this queue and it'll work as we expect. Yeah, so it's a queue. If we, however, put that into our list array, which is the one that operates kind of backwards, we'll see that our entire list of elements is in reverse. If we want to do the same thing with our array list, things are in order again. And if we're trying to put things in our heap module, we have to specify whether we want it to be a min heap or a max heap. If it's min, they're all sorted. If they're max, they're all sorted the other direction. Boop. So that's about how hard to use this library is. Cool. Yeah, so that is the library. And I get to these notes again. Yeah. So I didn't really go into how exactly these data structures are implemented. I think that conversation involves a lot of math and computer science that is pretty dry and boring. I tried to frame this conversation around the sorts of problems that we're solving, that you can solve with them, and where I would want to use these data structures in the hopes that maybe some of that resonates with you. And I think, honestly, some of the decisions I made around this library in terms of usability are more important than the actual performance gains I've been getting. I think some of the, so let me just cover some of these features. You notice that like the inspect panel showed a really nice, concise view of the queue. That took a little bit of work, but I'm like in terms of debugging, it's made my life a lot easier. It also just works out of the box with the enum methods. You can map over them. You can enum.into them. You can, it just implements the enumerable and collectible protocols, so they just works with streams. Now, obviously, the documentation is very lacking. It's mostly scattered handwritten notes, and it is what it is. But the overall architecture is pretty simple. We just have these usable Elixir classes, or modules, built off of a couple of core Erlang written modules that are the core data structure implementations of the specific type of heap and the finger tree. And as I mentioned before, there's no external dependencies, but I would like to talk about the NIFs, which I promised in the description and did not get around to. So I did write a NIF version of the heap module, and I was looking forward to using that in this because I knew it was going to blow the pants off of the benchmarks. But I no longer have access to that code. I wrote it while I was at my previous employer, so I haven't gotten around to rewriting it. There's a fair bit of finger wiggling that you have to do with NIFs to get them to play nicely across all platforms, and it does add a dependency to compiler tooling that goes beyond just like kind of basic Erlang. So maybe that's for the best. And I'm not sure that I'd want to use NIFs inside this like otherwise pure Elixir and Erlang library. I might make a separate NIF collections library first, but there's like your recommendation to use C. But yeah, so that's that. I think that's I'm still Shanti. I don't like money, but I do like not dying, and so if you want to give me money so I don't die, that's great. Let's see. Yeah, if you'd like to talk more about this and talk about the math and computer science behind this work, definitely check out these books and papers, Purely Functional Data Structures and the Finger Trees paper. Thanks all of you guys in the Elixir community and for letting me take the past 20 minutes of your life. No time for questions, I imagine, and thank y'all.